How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We present Tran, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. Tran presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIF matrix. Tran integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that lets users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduced the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the test to your requirements at the interactive testing section and observe them at the testing evaluation section.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
Hey everyone, welcome to our tutorial. We're going to be talking about the software system we created recently. It's both a system and a technique, really. We call it artifact-based rendering, and it presents a way for us to create data visualizations of 3D spatial data, and to display those either on your desktop Or what we most like to do is use VR or AR displays where the spatial aspects of the data can really pop. The key aspect of this new approach we call artifact-based rendering is that all of the building blocks of the data visualization are crafted by hand, hence the title, VR visualization by hand. So we want to show you how this process and the tools to support it work today, and we have a series of presentations as you see online. The first one actually will be by me, so stay tuned please, and we have a quick talk to sort of introduce the concept of this style of visualization and the tools, and then we'll go through a series of additional videos providing some detail. Then later in the afternoon, you'll get to actually use this. So that's what we're most excited about. Breakout rooms in the afternoon for really getting hands-on with the tool. Okay, so without any further ado, I think I want to hand it off to myself as the first talk in the series. And let's go ahead and roll the introduction to part 1. Hi everyone, welcome to the artifact-based rendering tutorial. We're going to hope to show you today how you can create 3D VR visualizations by hand. So translating work with traditional artistic media, clay, paper, paint, into a form where they become data-driven, interactive, immersive visualizations. My name is Dan Keefe. I'm a professor at the University of Minnesota, and I'm presenting this work together today with the Sculpting Viz Collaborative. This is a group of artists, computer scientists, and domain scientists who've been working together on this project for several years now. The roadmap for the tutorial today is as follows. I'll begin by talking just a bit more about what is it we actually even mean when we say VR visualization by hand. And then we've divided the remainder of the day into 2 parts. So in first part, we'll learn more about the software and the processes, even some of the design theory that underlies this work. And then in part 2, we'll actually use the tools. So we're going to run synchronous sessions in part 2 where we'll actually connect up to a server-based design architecture we've built to do collaborative VR visualization design. We hope you'll stick with us the whole time. Much of this work began motivated by this question. Would it even be possible? Could we design data-driven 3D visualizations in the same way creative visual thinkers like artists work now in their studios, the way they work with traditional tools like clay, paint, ink, and paper? And you might ask, well, why would you want to do that anyway? And I wanted to give you just 3 reasons today. One is broadening participation in visualization. In particular, 3D visualization, where often to be really creative in that space, it can require graduate level 3D programming skill. So we think if we can open up to a broader group of visual designers, that this might enable us to discover new solutions to visualization problems that we haven't even thought of before. I guess a more specific example of that, and the second reason, is to expand the visual vocabulary we use. If you take a walk outside in nature, or you walk through a museum, or even an artist's studio, the richness of the visual language that surrounds us really pops out. And if you think about the aesthetic of the data visualizations that we typically see, especially for scientific data, it's very sterile. It doesn't have that same richness. So we wonder if we can actually pull from nature, from the physical world, then we might be able to get a much richer visual vocabulary that actually leads to us being able to even encode more data. A third reason is to make our visualizations more approachable. We're in a time now where science itself is often under attack. How do we bring a more human relatable, engaging natural aesthetic to our visualizations? What if even the aesthetic of our data visualizations in science showed evidence of the human hand behind it? We think this might actually end up making science itself much more approachable. So with this motivation in mind, we've been working over the last several years to create this framework we call artifact-based rendering. And the big engine behind this, in terms of the computer graphics, was presented in last year's VIS paper session. And then we've continued to build on this. Oh, I should say also last year the design theory was presented in the arts program. This year we're continuing to build on this. You can see we've evolved to the web-based interface we'll use in part 2 of the session today. We've been interested in how we might evaluate the visualizations that come out of this methodology in terms of their capacity for human engagement. And in the Believe workshop, we'll present some humanities-style evaluation techniques for that. And then there's also a poster connected to our team this year, where we discuss how you can create auto-generated legends using these artifacts. So we hope you'll join us for these things, just some pointers to where this all comes from. What I want to do now is quickly go over the stages of this process we've developed. And step one, as I've alluded to, really comes down to getting in the studio, working with traditional tools, paint, clay, carving, thumb printing. We've looked at doing rubbings of natural textures, prints, taking photographs of friends' paintings, going out and photographing even just color that appears in nature. And all of these serve to create the visual language that is like the starting point for the data visualization. So we call those things artifacts, as in the physical artifacts that come up. And I should mention here also that as we're collecting these, it's not just like randomly go out and pick some flowers. Okay, we're actually thinking very deliberately about encodings. And one way we've helped artists to sort of have that mindset as they're working and developing these is to think about a structure like this. Thinking about encoding points, lines, surfaces, and color, and thinking about how those encodings might change based on whether you want to show a scalar progression, as in a magnitude channel, or sort of a categorical distinction. And artists get this. This is not difficult to understand from a visual standpoint. So this can often sort of guide the curation of artifacts. Once we source these from the physical world, the next step is to digitize them. And we've looked at a number of different processes for that, but we rely a lot on 3D scanning, especially for clay forms that might end up serving as glyphs in a final data visualization. We've used photography quite a lot. And there's a number of really neat things that might show up in the future, even lighting dependent appearance capture. I mean, really getting the reflectance, for example, of these surfaces. And then the next step is to translate those artifacts into a form that can be used directly by the computer graphics rendering engine. And this process can take different forms, but in a nutshell, we've created a series of web-based applets that allow you to upload the digitized artifacts and then do any tweaking that is necessary. Sometimes that's downsampling, sometimes it's like treating the image as a sample to then generate a longer infinite line texture like you see in this applet. We've also done work that allows you to, for example, indicate a forward direction for a glyph. So you're sort of priming these artifacts to be used in the computer graphics rendering engine. Then the next step is to use these now graphics-ready artifacts and connect them to data. And there's a special user interface we've created to do this. It's actually the focus of a VIS app paper this year because it's quite interesting from an artistic standpoint. It actually builds off the metaphor of printmaking, the way prints are put together with multiple plates and can be inked with different colors and so forth. So this user interface draws upon a printmaking metaphor actually to really quite clearly translate this problem of how do you map data onto visuals in a user interface form. You'll get to actually try that in part 2 of the tutorial today. So we're looking forward to showing this off to you. But this is the interface that creates that mapping from data variables to the visual artifacts. Okay, once that mapping is made, you then get your 3D visualization. We're just, as we get more and more into this, looking at the impact of the work, you can see just from some of the visuals, the aesthetic that's created is often quite different. But we want to understand like what's the benefit, if at all. And I want to point out one benefit we're really quite sure about at this point. It's basically the ability to rapidly iterate and explore new spaces in terms of the visual language for data visualization. So if your goal is creative design, this framework works really well, and we're getting results like artists working with this are able to explore 100 different visual designs in a day. And when we compare it to more traditional tools, we find this is just like a totally different ballpark in terms of the amount of rapid iteration and exploration of the design space you can do. Okay, of course that also has pitfalls. Maybe you're going in the wrong direction. But artists and designers are used to that, and they're happy to throw away 90% of the results and get to that 10% that are really spot on. So rapid exploration of design alternatives, really something really special with this. The final results can be explored in VR. They can be just shown on a 3D desktop as well. And some of the interesting comments we've gotten, for example, Phil Wolfram, one of our collaborators studying this data in the Gulf of Mexico, just gave us this quote, which I just absolutely love. Speaking of the visualizations, he said, "They look more like biology than they look like plastic. They could be real, produced by nature." And he says, "I think people are going to underestimate that. At first I'm perturbed. These don't look like plastic. And then I realized this is not a problem but a major benefit." And so we think this is part of what's so interesting here is the potential for the visual language to even connect with sort of a human element. This is nature. This feels right. And it's not sterile. It's just embracing this is natural. And that actually is quite different, but maybe it's time for some of that in our scientific visualization. So we invite you to try. Just to reiterate our schedule today, so the next session that's coming up is learning a bit more about these processes, and we'll start off with the demonstration of the user interface that I showed you just a quick picture of before. So you can see that stage of mapping data onto the visual artifacts. By the way, the artifacts themselves we store in an online library which is open for anyone to use. And And so in that demonstration, we'll be pulling examples from the library. So please join us for the next set of videos, and then we look forward to seeing you in person for the Use It session, where we really give all the software a good try. So by the way, this work is supported by the National Science Foundation, and we're really thankful to them, as well as the domain science collaborators who've provided some very high-end data sets, latest high-performance simulation involved in those, and we'll show you some of those today. You'll actually get to work with some of those data sets as well. So thank you so much. We'll look forward to seeing you throughout the day.
Hi, I'm Bridger Herman, a PhD student at the University of Minnesota studying computer science. For this portion of the tutorial, we'll be talking about the visualization design interface for the artifact-based rendering technique. First, I'll talk a little bit about the artistic metaphors we employ in the user interface, and then we'll dive into how to use it. When we built this user interface for visualization design, we were looking for a metaphor to translate the inherently technical computer graphics process for 3D visualization into something that aligns better with artists' creative processes. The metaphor we ultimately chose was intaglio printmaking, where many plates are inked and pulled through a printing press in order to create the final image. This is quite conceptually similar to the 3D computer graphics-based visualization process, in which layers like glyphs, lines, and surfaces are composited together in order to make the final visualization. In the design interface, we use this metaphor in two ways: key data and data impressions. Key data are the geometric representations of your data, points, lines, or surfaces, and can be loaded from VTK unstructured grid files. Each piece of key data has scalar and vector variables associated with it. These key data are dragged into what we call data impressions, or layers, in the visualization. We can then apply variables and visual elements to each data impression as we see fit. All of the data impressions in the center panel are composited together in real time to make the final visualization. Let's now move into a few demos of the user interface to show its capabilities. Here, we can see the three-part design interface. On the right, we have the design palette. On the left, we have the data palette. And in the center, we have the composition panel, where it all comes together into a visualization. Starting in the upper right, we have the plates, which represent the algorithms built by the programmers of the artifact-based rendering engine. Below that are the visual elements that the artist has imported from the Sculpting Viz library or their personal collections. These include color maps, glyphs, lines, and patterns. On the other side, we have key data and variables. Data and visuals are placed into data impressions in the composition panel to make the visualization. Let's walk through making a simple change to this visualization. So far, we have the Gulf of Mexico ocean floor with a color map applied to elevation, and a glyph layer that shows chlorophyll and salinity. The more chlorophyll, the denser the glyphs. So now let's say we wanted to replace the salinity variable with temperature instead. All we need to do is go over to the data palette and drag the temperature scalar variable over into this data impression, and the visualization will update accordingly. We can also double-click on the color map, and it will bring up a color map editor that allows us to create custom color maps based on the data values. Now, let's build a multivariate visualization from scratch, walking through the entire process from loading data to making visual changes to viewing the output. Let's first navigate to the design user interface in a modern web browser. I'm using Firefox. The specific URL for each breakout session of the tutorial will be provided later today, but since I'm running the ABR engine locally, I'll enter localhost:8000. We now see the ABR design user interface. We can start by either loading data or visual elements. Let's start with data. I've preloaded a dataset from the Filchner-Ronne ice shelf in the Antarctic that contains surfaces for the land ice and bathymetry, some streamlines for the ocean currents under the ice sheet, and glyph samplings for 4 water masses. Key data can be loaded by clicking the Load Key Data button in the upper right. I'll go ahead and add all of these key data pieces to our data palette. We can see them show up in our data palette as we select them here. Next, I'll want to import some visual elements from the Sculpting Viz library. I can open up the library here. This shows me the artifacts that have been curated by the Sculpting Viz team. I can drag and drop artifacts from the dialog here into the user interface. I can come back and get more artifacts at any time. Now that we have our visual elements and data, we can begin building the visualization. Let's open up a visualization viewer so we can see our work. The first step is to make a new data impression by dragging a surface plate into the composition panel from the plate list. You can choose what to do next. I'm going to apply some key data, but keep in mind that you can apply visual styles first if you'd like. You just won't be able to see anything until you apply key data, since these are the spatial registration. I'm going to go ahead and apply the terrain key data first. Notice how this puzzle piece fits right in to that. Notice how the data shows up with a default white color map. I'm going to filter the variables for those that are available for the Antarctic terrain, and we just have elevation. So notice how this highlights blue. That means that we can drag and drop that here. Nothing happens yet because we haven't applied a color map. Let's go ahead and do that. This one looks like a nice ice color map. Go ahead and put that in the color map slot. Now is a good time to save the state. So let's click this double bookmark icon to save the state as a new name. I will call this Ronnie-Demo1. And hit enter, and notice how our state name changes here. I can save over Ronnie1 at any time by hitting the bookmark icon. I'll now follow a similar process for creating the bathymetry. Now that I've got a draft of these two layers, I can collapse them and move them to save screen space. Next, I'd like to introduce some glyphs of the water masses to our visualization. Let's make a new data impression for the high salinity ice shelf water. First thing we notice is that, oh my, those glyphs are huge. Let's reduce their size. Next, let's apply a glyph from the design palette. Now, let's apply the temperature variable and an orange color map. I'm going to zoom in a bit to get a better view of these glyphs. Now, I'm going to edit this color map so that we can see the data a little bit better. So now we see the histogram of our temperature variable here. I'm going to go ahead and flip the color map around. And now I'm going to move our color stops here so that it fits the data range better. Now we can start to see much more variation in the visualization. I will now repeat this process for multiple glyph layers. After working on this for a while longer, we can make the streamlines by dragging a ribbon plate into the composition panel. We can apply the streamlines key data we can apply the eddy direction scalar variable. We can apply a blue-green color map. And we can apply a line texture. We may want to change some additional properties, like the line width, and the orientation of the ribbon. If we want to share this state with others, we can go to the Load State dialog and click the Download State button. We can also save high-resolution screenshots by going up to the camera icon here and clicking it, which will save the current view as a screenshot. Screenshots can be saved by going to the gallery icon in the upper right-hand corner and clicking on the thumbnail for a state. We've now seen how to create a visualization from scratch using the ABR design user interface, which leverages artistic metaphor and language to better align the visualization design process with artists' creative methodologies. By building the interface on top of the artifact-based rendering engine, the result also allows artists to bring color, line, texture, and form from their existing art practices to the world of data-intensive science.
Hi, everyone. So let's just pause for a minute here and see if there's any questions. I haven't seen any pop up on Discord, but we want to invite you to go ahead and chat in questions if you have them. So let's just give a second and see if that happens. I see there's maybe one coming in now. Bridger, while we're waiting for these to come in, why don't I ask you a question?
Of course.
Can you tell us, I know that you developed this user interface. What was the hardest part about developing it?
Oh, man, that's a really good question. I would say just figuring out exactly what features we need and what features are superfluous, if that makes sense. So what features are useful to artists creating these types of visualizations, and which features are just kind of fluff that programmers might feel like they need to add, but aren't actually necessary, if that makes sense.
Mm-hmm. Yep, that's tricky. Okay, and Laura asks, I'd like to try this on my own data. Is that functionality in the works?
Yes, it is. We have it right now where we can take any VTK unstructured data file, and I say any, this is still a work in progress, but we take a VTK unstructured data file and then turn it into the data format for ABR. Cool. So we have a Python script that does that.
Thanks, Bridger. We have one more question here coming in. Stravani asks, how does the key data look like? Let's say we want to visualize a location which is not real. How do we prepare the key data?
Yeah, so it all comes down to something using a software, say like ParaView, to create these unstructured data files. So we can either have points, lines, or surfaces. So those are all just geometric objects from VTK. So we can create those in software like ParaView based on like isosurfaces or point samplings from these volumetric data sets.
Great. So, good point.
Oh, yeah.
We see in the chat, Francesca sells more coming up. yeah, we're really excited to get this into your hands. So yeah, we'll tell you more about how to work with your own data and with the example data that we're going to try it on today coming up. Why don't we go ahead and move to our next talk now. Francesca Samsel, a visualization researcher and professional artist at the Texas Advanced Computing Center, is going to speak next. And you'll hear her talk about the design theory behind these visualizations where you have such a much larger visual vocabulary. Okay, so let's roll her talk.
My name is Francesca Samsel, and I'm a member of the Sculpting VIS Collaborative, as well as a research scientist at the Texas Advanced Computing Center at the University of Texas at Austin. I'm going to talk about creating custom artifacts in ABR, as well as designing with the expanded vocabulary that ABR enables. You've been introduced to the theory and principles behind the system and why it was created. And Bridget introduced you to how to use the interface to create visualizations. But I'm going to talk a little more about something abstract, which is design applied to visualization, and how to take this kind of racehorse of a tool and harness its power to get the results that you're looking for. The visualization on the left shows the Gulf of Mexico and the currents within it, and but more specifically the nitrate levels. And the same data is shown on the right, but is rendered in artifact-based rendering. And you can see how the system has enabled us to identify, extract, isolate a larger number of variables and physical properties within the water and depict them in one setting. In our system, the elements for encoding data are only limited to what you can create and capture, or borrow, or steal. This offers the potential for building more complex visualizations and the flexibility to enable one to direct attention, represent relationships, encode using intuitively associated representatives of variables. But as with all powerful tools, training wheels are helpful at the beginning. So I'm going to give you an overview of the range of options on how to make your own encodings, how to import them, and some guidance design on how to combine them. The types of custom encodings that you can make in artifact-based rendering include lines, color maps, textures, as well as the glyphs that you saw in the previous slide. Just to start giving you some examples of what some of these things might look like, on the left you'll see just a range of lines, different types of lines that we experimented with but applied to data. And on the right, you can see different surfaces or different textures that are applied to surfaces to indicate different characteristics or different properties, different types of materials within the data. When I'm looking to create a new set of lines, I start with just an open sketch pad and scribbles. And but through that kind of iteration and experimentation, I can pick out the few that actually might work on my data. And from there, you simply extract that part of the image, and it can be easily uploaded in the infinite line applet that you see on the bottom. When I'm starting on color maps, I often start from my collages, but you can start from any 2D material, photograph, whatever it might be, and drag it into the color loom applet down below and extract the hues from there. We'll talk more about that. Textures are extracted the same way from a two-dimensional image, and I will show you the details on that applet as well. I took this small collage and drug it into the color mapper, color loom, actually we call it, because we're weaving colors together. I love that name. And then you can see from the top to the bottom, I started out with a smaller set of colors and made just a kind of a variation on the cool, warm color map. But then I was interested in some other things, ones that came with a kind of a warmish gray with the blue, because I was looking at representing the bathymetry at the bottom of the Southern Ocean there. And then I was also experimenting with some teal and ochres. So you can see how with one source, you can easily make a wide range of palettes. Textures are interesting because once you start playing with them, the expanse of choices is endless. And they are worth experimenting with because some textures certainly work more clearly without distracting from the information of the data itself, and some are just a clear distraction. So after the break, you'll get a chance to either make your own textures or choose some from our library and experiment, and you'll begin to see how there are continuous textures that are more effective and others that are just a total distraction. Behind the idea of hand-crafted glyphs, as with all the other artifacts, is that you can customize the artifact to the characteristics of your data, making intuitive associations, or simply creating a set of visually diverse, easily distinguishable artifacts. 3D objects, either found, handmade, machine-made, nature-made, anything you can scan can be imported into the library. So here we're showing the creation of glyphs in clay up at number 1 on the top middle there. And then an image of one of the glyphs being scanned, number 2. And then 3 is the applet, which aligns the glyphs so that you can orient them in the desired direction. And 4 is the result. When you upload one into an actual visualization, this is what comes out in the legend, and you can see the pieces on the bottom right there. So the other thing about being able to create a broader vocabulary and your own vocabulary is that you can create categories, and that creates associations of different types of properties. So you can see that we've divided our system, the library within artifact-based rendering, into points, lines, shapes, and direction, because those are the primary properties of one design, and the direction comes from the need for showing direction in scientific visualization. And then you can see on the right how we make everything in families, so that if you want to create associations, if you were to encode, like 5 variables with the haiku kind of texture on them, they would be very distinct and recognizable as associative, as in contrast to the drum family. This is a visualization of the Gulf of Mexico, specifically nitrate levels, currents, and some other variables that contribute to propagating macroalgae for biofuels, which was the question these scientists were looking into. And you can see that there are different levels, and you can see how we've added one at a time, and that speaks to how one builds up a visualization in artifact-based rendering. And you can also see that we've kept the hue span of the variables within a narrow range so that other variables could be added on top, and we're going to talk more about that in the next session. So those are a lot of complex elements with a lot of possibilities, and it can be a bit overwhelming, but we're going to walk you through some trials in the next session, the next half of the program. I would like to point out one thing, that the system really was designed for VR if you've got large three-dimensional data. When you put on a VR headset, all of a sudden the whole palette, the structure, the location becomes much clearer. And so you can create actually much more complex visualizations that are easily discernible in VR, whereas not so much in 2 dimensions.
In this video, we'll learn how to use the Sculpting VIS applets to turn handcrafted artifacts into computer graphics elements usable in artifact-based rendering, or ABR, visualizations. We'll start by navigating to sculptingviz.tac.utexas.edu, where we'll land on the home page, where the Sculpting VIS applets and libraries live. The library is where the artifacts go when uploaded from the applets. So we're just going to go ahead here and open up both pages. In our library, you can see we have all of our glyphs, color maps, textures, and lines. Each of these categories of artifacts has an associated class, which are these labels along the top, and family, which are these labels along the side. We can see each unique category for color maps, textures, and lines.
All the elements you see here are part of our curated library with recommended artifacts ready to go. Now, on the applets page, we have several options to choose from. We'll start with Color Loom, the applet used to generate color maps used in ABR. This is our empty canvas in the middle. We can drag up to 4 images into this workspace from a file manager. As an example, I'll open up my file manager here and drag and drop these 2 images into our canvas space. As you can see, Color Loom has automatically picked a series of colors from the image for us. We can click and drag these over to the right side, where the program will interpolate between the chosen colors, creating a color map. If we don't like the way a certain color looks, you can simply click on a swatch and hit the delete button, and it will be removed from the color map in the right-hand panel. If the automatically picked color isn't quite right, you can hover over the swatch in the canvas workspace area and then come over here to the left and adjust the HSV sliders, which will in turn change the swatch to your desired hue. We've adjusted this color to appear a bit more blue, so now we can drag and drop it into the color map builder space. If we're happy with that, we can go up here to Save to Library. A window will pop up asking you to decide on a family and class for the new color map. So here, let's say it's in the blue family and the linear class. Click OK, and your new color map will appear in the library. Our next applet is the Glyph Aligner. This applet is great for creating 3-dimensional, directionally sensitive glyphs to be used in the ABR interface. Typically, we will 3D scan the glyphs using a 3D scanner or photogrammetry application. For now, we've prepared a test.obj model for this demonstration. We can drag it into the window and see the example glyphs change to reflect the new 3D object. Our goal here in this left window is to align the forward direction of this object with the dotted axis that says forward here in this cube. We can use our right mouse button to reorient the cube until the forward axis lines up with the forward direction of the glyph, which can be wherever we want. Here, the left mouse button allows us to move around and make sure we've aligned the glyph with the axis sufficiently. Now that we have our glyph aligned, we can see on our preview visualization over here on the right that our column glyph is correctly aligned with the directionality of the data. Next, we want to render a quick thumbnail. This is what we'll see in our library when we're looking for our glyph. Get your glyph set up to the desired alignment, then click Render Thumbnail. Finally, we need to choose the glyph's family and class. Let's say this one is in the Direction class and in the Box family. Click Export.obj and your newly aligned glyph object will appear in the glyph library. Next up is the Line applet. We can use this applet to create streamlines or ribbons in ABR. The idea behind the applet is to allow a user to create anything they want outside of the program, any texture or ink wash, and then drag it into this applet, which will automatically generate an infinitely repeating version of that pattern, which can be used as streamlines in a visualization. By default, this box is checked that says nothing fancy, just repeat it. The texture loops top to bottom, so it begins at the top and then again at the top, etc. Perhaps we'd like to introduce some randomness to our custom streamline. By moving these sliders around, we can change the character of the line until we find something we want. When we're done, we can once again use our family and class categorization to save the new line to our library. Finally, we have our texture mapper applet. The texture mapper is used to create a variety of surfaces for the artifact-based rendering engine. This applet is quite flexible in that we can use any image to create a texture, as long as the image is a .png file. So we can just drag and drop this simple image here and use the crop window to find the area of texture we want, and that's it. Pretty easy. Once again, we can save to the texture section of the library by choosing family and class and then clicking export. That's it. Thanks for listening.
Okay.
Good afternoon. I see we have a question coming in. Just to give you a brief overcap. Could you share that URL here? Yes, we can do that. But I see, Laura, we're getting there. We're getting there. We're trying, it's coming. So that was a brief overview of the applets. And just to give you a sense of what's coming, I'm going to do one more thing on design, and then Greg Abram is going to talk to you about data and importing your own data. So that's what we have coming up, and I will share that URL with you. And unless there's anybody else, I think we can play the next video.
Great. Well, I'd say let's move on to the next video. I don't see any other questions right now. We'll have a chance to, after we see this whole series, to do some more Q&A. So let's move on to the next one, which is on collecting and creating artifacts.
In this section, we're going to discuss how we bring scientific data into Sculpting Viz for visualization. In earlier sections, we discussed how we bring in artifacts used for visualization.
Looks like maybe we missed a video.
And so forth.
Yeah.
I think there's...
The one that you pulled up, that's about data, and then go back to one more about design. Not the end of the world.
Yeah, no problem.
There you go.
Artifact-based rendering is a pretty powerful engine, and it allows you endless options. So then the problem becomes, how do you choose between those options, and how do you select specific either glyphs, colors, or textures that are going to help you meet your goals with the visualization. So to that end, I've put together a few guidelines, and that's what this section will cover. So the first thing to consider is that what we see when we look at a visualization is determined by the contrast between the elements within the visualization. So what abuts what is really important, especially in scientific visualization. It's important to consider because that's changing all the time as the data is moving the elements around, especially in obviously time-varying visualizations. So the first thing you need to know is something about the contrast. And in terms of, we're going to talk about three kinds of contrast. We're going to talk about color contrast, we're going to talk about shape contrast, and then we're going to talk about profiles and characteristics, some of the more subtle elements that pertain to artifact-based rendering. Many of you may have studied or heard me talk about color contrast theory, but the main thing I want to talk to you about here is that think about light and dark and cool and warm. The first thing I do when I'm developing a new visualization is I create a guidance style sheet for myself. So I type up a sheet and I list all the variables and I decide, what's related to what's most important, and then I assign it colors and shapes. And here's your chance to assign it shapes that are analogous to create categories, or colors to certain variables to create emphasis. What is important to know is that your style sheet is a guide. It's not a solution. And that when you've got this many elements in a visualization, the impact of one on another is important, and it takes a little bit of juggling. Before we start a style sheet for our visualization, I'd like to go over the glyphs and color maps and textures and things that are in the library, specifically with an eye towards design, and just give you some guidance on the types of contrast that we have found are effective within visualization, because often there are a lot of elements that are, kind of creating a big plate of spaghetti and meatballs. If you open up the glyphs section, for starters, You'll see things are divided into lines and points and then just other kinds of shapes as well as direction. So there are three areas of contrast that work best. And one is a contrast of profile. So for instance, a point versus a line is going to be a high contrast of profile, whereas a disc versus a point, like a disc shape, the drum is a disc shape under point, and clay rice is a sphere shape under point. Those are going to be less, the contrast will be less dramatic, and thus, if you've got a lot, will be harder to tell the difference. And the other type of contrast to consider is the density of the texture. So for instance, a haiku is a low density texture, as is the geo, whereas the drum and the tricarved are high density textures, so those are going to contrast. In common visualization programs, we're used to seeing a variety of glyphs, be it cubes, spheres, or arrows. It's a small list, but there is some variety. Lines are a different animal. A line is a line, and you can vary its thickness, or you can make it a tube, but pretty much they're the same. But if you take a drawing class, the first thing that they're going to talk to you about is line quality. And so that's where the section on lines comes from. And I'm going to show you just a few examples of the possibility of line to distinguish between different variables or different, what I call, pieces of spaghetti. I could talk a long time about types of line and variety of line and how to make distinct lines, but basically there are a lot of different kinds of lines, and it really depends on how dense your data is, what variety you can use. Often the simpler ones are better and still can be very distinct. The last category is texture, and these can be textures for isosurfaces. They can be textures that go on different properties to make categorical associations between different materials. They can be just an abstract to give you a contour of the form, or they can be associative to reflect, water or smoke, whatever it is you're representing. So a lot of possibilities, but they're quite tricky. And so the first thing to know is that they are effective, especially if they're small enough and light enough. And ABR lets you tune the opacity so that you can kind of tune them down a bit. And just a small bit of texture, even a light opacity, goes a long way in distinguishing between different isosurfaces. It's really helpful. But you can get in trouble because they're quite beautiful, but often they're disturbing and distracting in and of themselves. So it's always a balance. And like everything else, it's a balance between looking like it's encoding data versus adding texture and richness to the image. With that as a primer, let's go ahead and get started, and we'll see what we can piece together. I'm going to start off with an example that kind of clearly shows you a number of different kinds of contrast. You can see the little, I'm going to call them the gray legs floating around in there, and they're very distinguishable against, say, the maroon discs and the green balls, and then the eddies that are going every which way. So, but when we pull something up in artifact-based rendering, Bridger showed you the interface, so I'm just going to stick with the images themselves. You're starting with a blank slate. This actually, I've already put a color map on the bathymetry of the bottom of the ocean. So this is the Ronnie-Filchner ice shelves actually, or the ocean underneath the Ronnie-Filchner ice shelves, and a little bit of the Southern Ocean off of Antarctica. Here in this data set, I have 5 different water mass types, which I'm representing with glyphs. I have eddies moving in a couple of directions, and I need to keep them all separate because there aren't a lot of relationships between them. Often, if I'm looking at phytoplankton or zooplankton or whatever, we'll have a clear distinguishing categories where we can identify which kinds of glyphs we're going to use, but that's not the case here. So I started on the left, and you can't really see it, but it's the green, and it's around the top. I call those little guys haiku, the top one on the 4x4 square of glyphs. And that's all fine, but I knew I was going to be putting some other things right on top of it. So I knew that I needed a high profile contrast. And so I moved over and changed that to a line like you saw in the gray in the last image. And but then you can see, as in image B, it does not show up very well. So because there are lines and they're thinner, you need a higher degree of contrast. And then in C, the only thing I did was I changed the green color map. And so you can see I have a set of greens there in color maps above C. And you say, well, why does she have so many? And the difference between B and C is only the color map. And that's why I have so many. So after I settled on the green, I'm going to call them green spikes for the cold deep water, I was going for the next water mass, which I knew was going to sit kind of on top of that other one. So I wanted a more of a curvilinear form, and I wanted something that was more round, not long and thin. And on the left, this is what happens when you put on the variable. Sometimes it comes up big, sometimes it comes up small. You have to resize it. But before I did that, I wanted to see what kind of texture I was going to be ending up with. So the image on the left is what you get right away. The image on the right, I put on a kind of a clay glyph. It's just a minor twisty point, I call them. And you can see right away you get a kind of a texture. And then on the left, what I did was I put on a color map without a variable, okay? So you get a very uniform color across it. And on the right, I put on the temperature variable. So that made some of the glyphs lighter and some of the glyphs darker. But of course, you've got this huge sea of glyphs and you can't see anything else. As I mentioned before, a style sheet is just a first starting point. As you can see, the contrast between the green and the light goldy yellow glyphs here is just not going to do much good. So I bumped up the contrast there and turned it into a more brighter orange, which differentiated the different variables along with you there. And that one you can see how you've got a profile difference too, which also accentuates the change. And then the last thing was the real focal point of this visualization were the eddies. So there you can see them in red on the right-hand side. So you may say, well, that looks pretty easy. And, that one wasn't too bad. But the reason I brought up all these points about contrast and whatnot is that when you actually get into the guts of a moving visualization, it gets a bit tricky. And every piece of your visualization, be it the color map on the bathymetry or the shapes of the glyphs and where they move over time and how that contrasts with the background, is going to have an impact on what you can and can't see. So what's interesting about the slide here is that the only difference between the one on the left that we're working on and the one on the right is the bathymetry blue. And you can see that it washes out the vibrance of the whole visualization, but more importantly, it obscures the pieces that are shown on the right-hand side there. So basically the problem with the one on the right-hand side, which is now on the left-hand side of this slide, is too little contrast. They're all in that sort of pastel-y, cool range, and there's not a whole lot of contrast. So, but you can also go too far. And on the middle image, it's a very subtle change in the color map. It's just a turquoise map as opposed to a kind of a muted blue. And it's way too much saturation. So what you've got is you've got the attention on the wrong part of the visualization. You've got it on the bathymetry, and especially in that part of the ocean. It's not that interesting. So that's why the one on the right, we had a fair amount of definition, and the light and the dark distributions were calculated to fit the glyphs. So just a few other things to watch out for. There's a lot of research that says be very careful about the semantics of your color. And so I tend to stay away from things like lavender and pink, especially if I'm dealing with the ocean, and try to stick with colors that maybe have some resemblance. But then on the right, I did use a blue, and but it just overwhelms. It overwhelms the water masses, which are what's important. So here you can see actually the one that I finally settled on. It's a little garish, but everything is very clear, and that's the goal. To wrap this session up, I would just say be patient. It takes a lot of trial and error, even for someone who's experienced with design. Take your time and have some fun.
Okay, thanks everyone. Any questions at this point? Please feel free to ask. You can type right into Discord or the chat on YouTube. And let's see, maybe as we're waiting to see if anyone has questions, I could ask one. So I'm interested in particular, and I mean, we saw some of it in this video, but also in the last one, you talked about
in this section
families of glyphs and things like haiku and drum, and I noticed those words.
Yeah.
And so tell us, do the names tell you something about when you use them? What do those names mean to you as an artist? I mean, I want to understand how you think about them.
Okay, so the families are meant so that you can create categories and that relate to the science variables. Like if everything is in plankton, maybe you want all things that are round, and if everything is in metals, maybe you want one of those little ones that are multifaceted. But the names come from the haiku. It's if you notice, there are just a few deep, sort of very purposeful lines on those shapes. And that, to me, aligns with a haiku. Yes, sparse, but definite. And the drums, that actually is not made by me. I have a good friend who's a drummer and a ceramic artist. And so I brought him some clay. I said, okay, your turn. And he was like, so those are the drums. That's all. Wow. The other thing I do want to point out is I did post for folks, if you're interested in looking those over. I did post what we call the library and also the applets so that you can play with those, and those are in the Discord chat. And then next coming up is how do you work with your own data. So why don't you roll that last one?
In this section, we're going to discuss how we bring scientific data into Sculpting Viz for visualization. In earlier sections, we discussed how we bring in artifacts used for visualization, glyph geometries, texture maps, line types, and so forth. Now we're discussing the scientific data itself, the underlying data that we're visualizing. Here's the big picture. Data for scientific visualization generally comes from a simulation running on a large-scale parallel server. One such example is WRF, a widely used weather simulation code. From various inputs, including so-called boundary conditions, WRF evolves a model of the weather through time, producing datasets that, for example, tell us the temperature, humidity, wind direction, and velocity everywhere in a region of the atmosphere at a set of points in time. From this raw data, visualization programs run algorithms that produce derived data products which, when rendered to images, allow users to understand the simulation results. Examples include slicing the data and color mapping the results, or placing little arrows periodically to show how the wind flows. You can see such renderings on the Rendered Weather channel. ParaView is one such visualization system, capable of taking large-scale simulation data, deriving renderable imagery, and then typically rendering it. Here we will see how we use it instead as a pipeline stage, preparing data for subsequent rendering. Here this rendering is done by ABR, running on a high-powered single computer that is capable of attaining rendering speeds sufficient for virtual reality use. Now let's look at how we create these renderable data products derived from potentially very large raw data and get them into ABR for display. The basic input format is the VTK unstructured grid data type. Unstructured grids consist of two parts, the geometry describing the three-dimensional form of the data, and values that are defined on the geometry. Sculpting Viz uses the term key data for this geometrical information and refers to the values defined on the geometry as variables. We support three basic geometrical forms, all defined in 3-space: surfaces, path lines, and points. These are specified in a VTK unstructured grid as a set of vertices and a set of elements, or cells, that link the vertices together. For example, surfaces are sets of triangles that are defined as lists of IJK triples that list the vertices that comprise each triangle. Similarly, path lines are derived as arbitrary length lists of vertex indices. Points are simply single vertices. Data is defined on the vertices of the dataset and interpolated in between. Single values for scalar variables, for example, texture or humidity, or 3 tuples for vector variables such as wind direction. All will be represented as 32-bit floating point numbers. There are lots of ways to create VTK unstructured grid objects and export them to VTU files. VTK is a C++ class library, and there are bindings for many languages. I use VTK inside Python for a lot of work. However, the most straightforward method of creating VTK unstructured grid datasets is to save them from ParaView as VTU data files. While we can't really teach ParaView here, we can give you an idea of what's going on. Here we see ParaView in action, having imported a weather dataset from WRF. ParaView enables the user to derive renderable data objects from the original input data based on parameters that the user can set. Here the user has used several ParaView filters to create a visualization of the data that consists of surfaces corresponding to clouds, an elevated terrain surface, and some streamlines that show particles as they're carried by the wind, another variable in the dataset. These visualizations are built up of pipelines of ParaView filters. Here we see the ParaView pipeline browser. The pipeline browser shows us the sequence of filters being applied to the data and gives us the means to alter and extend these sequences. Here's a close-up of the pipeline browser showing the 3 sequences of filters being applied to the WRF data. At the top we see the original data imported using file points to open and consisting of a time series of datasets, the variables describing various properties in the atmosphere over the western United States at a set of points in time. Then there are 3 sequences of filters, generating the derived data that you can see in the resulting visualization. The last filter in each pipeline has an open eye, indicating its visibility in the result. And here is the resulting visualization. You can see the 3 different derived datasets rendered: the lofted terrain surface, the cloud surfaces, and the streamlines. Unfortunately, each of these 3 pipelines creates as a result as polydata objects, a much older data type that has been superseded by the unstructured grid data type, which has not been thoroughly expunged from ParaView. We can convert these polydata objects to unstructured grid objects by simply passing them through the append datasets filter, which we've added here at the end of each of the 3 sequences. Once we've converted the derived data objects to unstructured grid format, we can write them out to disk. With an append datasets filter selected, use the Save Data button to write the data out. A file browser will appear. Give the output files meaningful names. I used wrfclouds.vtu, wrfstreamlines.vtu, and wrfsurface.vtu. And note the directory where you put them. Now, in that directory, run the vtk to abr.py Python 3 script on them. This will install the data into ABR. Note that this must be done on the system where the ABR engine will run. If the data was generated on another system, it will have to be copied to the ABR host first. Now with the ABR engine running and the ABR GUI up, hit the button that looks like an SD memory card. This will bring up a dialog showing the available datasets. Here at the bottom, we see the 3 datasets we just imported. Note that the names of these objects comes from the names of the original VTU files. Hit the crosses next to them, and they'll be activated into the list of active key data objects. And here we see them in the key data pane of the ABR GUI, and we can now use the ABR GUI to show them in many, many ways. This process is a bit clumsy, however. We had to create the VTU files in ParaView, we had to write them out, potentially move them to the system hosting ABR, and run Python scripts to install them. We could streamline this by attaching ParaView directly to ABR. Here's my setup at home. On the left is my Mac, where I do almost all my work. On the right is a Windows system that will be running ABR and driving both a desktop view and a Vive head-mounted system. I do all my real work on the Mac and just use the Windows system to host ABR. Let's see how. Back in the pipeline browser, we add an additional filter to each of the 3 pipelines that produce derived data. In the property page for each of these, we tell it where to send the data, here the IP address of the Windows box. I'm sure I could do this by host name if my home network was set up properly, but this is easy. We also give the data objects a name, analogous to the file names we used earlier. When we run the visualization in ParaView, the objects will be transferred from ParaView on the Mac to ABR on Windows and installed in ABR using the given names. And there they are in the ABR GUI on the Mac display, and the results show up in ABR without interacting with the Windows system at all, other than running ABR to begin with. And the best part is that the connection persists between ParaView and ABR. Recall that this data was a time series. If we hit play on ParaView, it will iterate through the time steps, produce derived data sets for each time step, and send them to ABR. ABR receives them, and in a time step synchronous fashion, updates the visualization. Here we see the ABR display as ParaView iteratively loads in a time step, derives the renderable data objects, and transfers them to ABR. ABR understands that the data is updated, and when all data products for a time step have been received, updates the display. Note that until that point, ABR remains actively rendering the prior time step, giving the user the effect of smooth motion, periodically updated with new data. In summary, we have shown that the basic input format for scientific data into ABR is the VTK unstructured grid object format and how it can be loaded into ABR either manually from saved files or received directly from ParaView, which can be running anywhere, firewalls permitting. We have driven ABR directly from the TAC supercomputers in this manner. And with that, I'll call for questions. Thank you.
Okay, thank you, Greg, for that talk. And wondering, does anyone have questions on the getting your data in that Greg just discussed? We can also take at this time really questions for anyone in the group, as we're sort of now wrapping up the part 1 of the tutorial. So if there are things on your mind, please type them into Discord, and we can we can relay them to the presenters.
Yeah, there are questions. Why don't you talk about where they might find instructions? There'll be instructions on your web.
Yeah, we'll be preparing instructions online at some point pretty soon, I'm sure.
Where's the?
On the Sculpting Days webpage.
Mm-hmm. Yeah, it doesn't look like we're having many questions.
Alan wanted to ask something but got shy.
Say again?
All right, so why don't you wind it up saying?
Who was that just seemed to ask a question? I didn't quite catch it. No? Okay, it looks like actually maybe some are coming out now with through typing. So let's see. Let's see what those are. And let's see, as we're waiting for that to be posed, Greg, maybe I can ask you a question. So I'm wondering, it looks like a lot of what you've set up in this, like seeing your workspace actually underscored this, is really organized for, I mean, pretty high-end data sets here. A lot of stuff is large data, multivariate, pretty complex. Is there a pathway that's like more of a, I don't know, single computer setup that also works here?
Sure, nothing that I showed you there is anything that can't be done on a single computer. We can, but the beauty of it is that we can run way beyond our single computer. And when our newest enormous supercomputer at TAC, Frontera, was inaugurated, we were able to demonstrate simulation code running on Frontera, talking to ParaView, talking to ABR, and basically getting a real-time view of what was going on inside the simulation in virtual reality. And the NSF guys kind of like it.
So talk about simpler data. What if you have simpler data?
Well, anything that you can run in ParaView, you can really do this way. So, ParaView is an application that you can run on your local machine. You can bring in your own data sets in ParaView. ParaView has an enormously rich set of tools to convert your data to these data products that we can import into Unity and put up in ABR. Once the connection is established, will other data extracted in ParaView be automatically propagated to ABR? Is there a plan to support other data types, vectors, and tensor data? We do support vector data. We aren't currently supporting tensor data, but that's a particularly interesting one because of some other work that they're doing at the University of Minnesota. So I suspect we will be looking at that sometime in the near future. No, basically you set up a ParaView network, and then you identify the filters in ParaView that are producing the data format, the data objects that you want to view in ABR, and you attach a special filter to them. And it's that filter's job to push the data from the ParaView world across to the ABR world. Does that answer the question? One thing that I don't think we've really hit heavily enough in this presentation so far is that while we're seeing this stuff showing up in 2D here on the screens, the real excitement is showing this stuff in virtual reality. And you can basically take one of these things that we're showing you how to set up now, and you put on we use a Vive, and it is the coolest thing in the world, I gotta tell you.
Okay, so come back and after the break, because it's your turn to be able to move around all those things.
Okay, we'll see you in a bit.
Folks, I'll just emphasize or sort of restate the plan. We've got a break now for the next half hour. And so come back at, depending on your time zone, but come back at the top of the hour in about 34 minutes, whatever time that happens to be for you. And we're going to jump right into actually using this when you come back. We'll set up some breakout rooms, and we have multiple instances of this engine running remotely. And so each breakout room will get to use one to actually design some visualizations. So take a break and then be sure to join us for that hands-on aspect, which will be the most fun part. Okay, we'll see you soon.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
Visualizing class separations is used in applications such as classification and clustering. However, many dimension reduction techniques are limited due to the issues of separability and interpretability. We propose a visual analytics framework to support the exploration of nonlinear complex separation structures with the power of locally linear separations.
String graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign Lorentz through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the string graph layout optimization. The result shows that our algorithms perform better than the others.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results. For example, the Mahanoda-based brush and the CN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
Text alignment is a fundamental technique in many text-related domains. In this survey, we cover 3 text alignment scenarios: collation task, text reuse detection, and translation alignment. On the basis of those scenarios, we reviewed the existing text alignment visualization approaches and discussed their advantages and drawbacks. We finally derived design implications and shed light on related future challenges.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift. To handle the concept drift, we developed the Drift VIS, a visual analytics system to help the expert understand when, where, and why the drift happens, and update the model to improve performance.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained data path extraction method, a river-based visualization, and a contribution analysis method.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error.
than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAV, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We present Tran, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. Tran presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. Tran integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Attention mechanisms have greatly improved the performance of many language models. Yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present Strat Graphics, an approach for designing data-agnostic and fully reusable visualization templates. Strat Graphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
Suppose you want to see the overall structure of a new project repository. Using Git client tools, GitHub Network, or Git log command, it's quite burdensome to get overview and navigate data. We presented Githru as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
Hey everyone, welcome back to part 2 of the tutorial. Thanks so much for joining us again. And this is the part of the day where we're going to actually use this system live. We're going to ask you to join some breakout rooms in a little bit. And so let me just give a quick overview of the schedule. Just a couple minutes here of introduction to how this will work. Then what we're going to do is walk through a live example of building a visualization with real data. And then that example will end up being the jumping off point for your breakout room. Okay, so it'll be sort of a walkthrough. We'll talk out loud as we're developing this visualization. And then we'll have about 7 breakout rooms going in parallel. And each one will have a host from our team who knows the software and can walk you through it. But you'll have a chance to actually drive and create the visualization using the web-based. Just so I can't remember if we already mentioned this, but basically we are running a remote system. So we have on the Stampede supercomputer at TAC, we've got nodes that are running this software that we're connected to, and we'll assign 1 to each breakout room. So you'll get a chance to do that. Now, if we were live and in person, as you were making these modifications to the visualization, you could just pick up your headset and look at them in VR as well. So we want you to have a sense of that being, a real immediate ability to see this in 3D. And then also, if we were live, in person, we would send a group of you outside to do a nature walk and find some artifacts to bring in. And we'd have a table with paints and colors and things like that. So people would be making visuals to scan and bring into the system as well. Today, we're going to use the curated set of artifacts in our library that we've already done that with. But we look forward to, hopefully if you like this, we can talk more and you can try bringing in some of your own work as well. Okay, so to jump right in, really the first thing to do is to just give a quick intro to the example data set that we're going to be working with. This comes from colleagues at Los Alamos National Laboratory, and they're studying the interactions between ocean water and Antarctic ice. So we're going to be looking at the Southern Ocean near and under the Ross-Filchner ice shelf. And then you'll see this is framed by the bathymetry, the seafloor, and the nearby terrain. Okay, so that's the basic setup. And the scientists are interested in seeing different properties of the ocean, including the flow in and out of the region under the ice shelf, and the location of the so-called water masses. Okay, so these are regions of the ocean that have particular properties of salinity, temperature, and depth. And we will be looking at those using this visual language of color, glyphs distributed in space, things like that. And we should say that we're not so interested in the precise boundaries of these water messes, but more in their general location. So this is a case where sampling and use of glyphs to represent them can make a lot of sense, because you avoid some issues of occlusion if you're doing more that you would find if you're using a surface or volumetric representation. Okay, so that is the very quick overview. And what I'd like to do now is hand over to Greg Abram, who is going to run through sort of a step-by-step example of how we get started with creating this visualization. And again, that'll become our jumping off point for each of our breakout rooms where you get to do the design yourself. Okay, so Greg, why don't you take it over?
Okay, is it going to bling me up here at some point? Technician F.
So, Ein, could you make Greg the full screen presenter now?
You need to share your screen too.
There we go. Nope, that's Technician F. I'm Greg Abram. I was thinking that it was, well, actually right now it says host disabled participant screen sharing. Okay, looks like it's working now. And I am just going to focus in. No, I'm okay. Okay, so I think you are now seeing with a little luck, I'm sharing the screen. Can somebody confirm that?
Yes, you're sharing.
Okay. So, yes, as Dan described earlier, this data has to do with people who are interested in understanding the interaction between ocean water and the ice sheet, because they're concerned that the flow of water and the warmer water in from the outer ice sheet participates in melting the ice shelf from underneath. And this is their data. So here what you're seeing is the on the outside here is the terrain of the nearby parts of Antarctica. This region here is the ocean data. The ice sheet actually extends about to here. Okay, just a second. I'm told I need to change my sharing here for a minute. Give me 1 second. So we will just focus in on this part. There we go. Still sharing? People seeing it? Somebody say yes.
Looks great.
Okay. Okay. So what we're seeing here then is the floor of the ocean, the nearby terrain. These colored areas here you're seeing are glyphs that are representing these different so-called water masses. And this tangle you see in the middle are streamlines that are showing how water flows across the entrance to the ice sheet. So the ice sheet actually comes out to about here. Then the continental shelf is this big change you see here in color. And then this is deep water up here. So that's kind of where we're going to be wanting to go. So this is meant to demonstrate the raw data and what we can possibly achieve using this system. So now I'm going to go through steps that should lead us to being able to do that. So I'm going to clear this state entirely. I'm going to grab the so-called talking stick and now clear the state entirely. And hopefully, there we go. So now we've cleared the state. So as we've talked about before, the key data sets are available under this button up here. I can select the ones that I want. In this case, I'm going to want them all. And you can see as I do this, they get highlighted over on the left. Let's see, we got 9 of them, 5, 9, 1, 2, 3, 4, 5. Yep, got them all. Now we can hide that. Now we want to put up surfaces for the terrain. Before I really get heavily into this, let me just say anybody who's ever give demonstrations live should be aware of the gremlins of live demonstrations. And we're really running sort of a high wire act here. So, forgive me if things get a little clumsy. I'm interested in what variables are alive on that terrain. So I'm going to click that, and elevation is the variable I want to color by. And over here on the right, let me make this guy a little smaller. Don't seem to be able to. I thought I could, but I can't. There we go. I'm going to choose a color map for it. Here are the color maps that we chose up front to put in our local palette. And I'm going to use that color map to make the terrain look a little more interesting. I'm going to pull up another surface to do the bathymetry. I'll connect bathymetry to it. Here we are down here. Now the data that is relevant to bathymetry is bottom depth. I'm going to color the bottom of the ocean based on how deep it is. And we can select a color map for that. I'm going to choose this one. And I'm going to drop it right there. And now that looks interesting, but I want to make the bottom of the ocean look a little more kind of textured and have a little more sort of character. And so let's see, I'm going to pick a texture to drop on the bottom surface, which looks good. I like this one. I drop this on the pattern guy. You see the magic little pieces fit together. And now you can see that there's some texture been applied here, and I can affect the basic size of the that's being mapped on there. So make it a little smaller so I get more repetitions of the texture. And now I like that because I think that looks kind of like the whatchamacallit, the caustics on the bottom of a pool when you're at home, if you have a pool at home. Okay, let's add in the streamlines. I'm going to use the ribbons plate and add in the streamlines. Streamlines here, oddly enough, are a really, really big data set. There's a lot of geometry in those. And so it can take a minute for those things to load in. Now let's see what variables we want to use. Angular eddy direction is a good one. Eddy direction is really good because the scientists are interested in eddies, whether they rotate clockwise or counterclockwise. And so using this variable, we can color using a divergent color map. Francesca will be really pleased by this, I'm sure. Come on, scroll. Why isn't it scrolling? There we go. Yeah, we don't have any. Oh, this one would be really good. Oops, I dropped it. But I'll use that divergent color map. And now parts of the thing that tend to be turning clockwise will tend to be the bluer side, and that tend to rotate counterclockwise will tend to the orange side. And we can change the by rescaling the color map. Come on, you can do it. Okay, maybe it's not going to be happy with that. Just because Stampede is an enormous computer the size of my house does not mean it's particularly fast at doing any particular thing. All right, well, let's just let that go for a minute. But I am interested in putting a line texture onto it. Here are my options. I like this one. So I'm going to drag that here, and I'm going to drop it on there. That makes them a little hard to see, I must admit. So let's try a different one. That's a little better. And now if we take a closer look at this thing, keeping in mind if I do this in, I can do this in the virtual reality space, and this all happens, you know, super fast. Come on, there we go. Going the wrong way. I wanted to look at it more, what's the word I'm looking for? Tangentially. There we go. And let's rotate it around. Now, if we zoom in close, keep in mind here all of the, so we are doing a texture cutoff, huh? This thing has all sorts of capabilities that never fail to amaze me. So you'll have to forgive me if even I don't drive it really well. Bridger is the professional. But anyway, I've been able to use Francesca for me. Okay, so now we want to add in some glyphs to show these water masses. So I add in a glyph plate. I choose a water mass data set.
Shrink your lines and be less detailed.
That looks a little better. Now, my initial glyph sizes are way too big, so we're going to make that more like 0.5. I have a backseat driver here. Now those will go back. The glyphs default to little spheres because we have to have them default to something, but we don't want to use little spheres, so I can use, say, this glyph here, and I can drag it up and drop it on there, and you will see that the glyphs change shape. We can add another variable on there to show, say, temperature at each one of those grid locations. And of course, we have to attach a color map to interpret the temperature. And so now if we tip this down again a little bit and zoom out, we can see where the AASW water mass is, kind of inshore under the ice cap. So that's basically the idea, and I hope I've given you the sense of how you add plates, you attach data sets to the plates, you attach visual attributes to the plates, and you get really pretty pictures. So now I think, correct me if I'm wrong on the technical side, we are going to expand this out and break people down into 8 different breakout rooms, each one of which will have their own canvas here. And how is that happening? Can anybody tell me what to do next?
So I don't know if I'm being heard by everybody right now or just you, Greg. But what we want to do is have everyone join us on Zoom now, and then we can assign breakout groups. So basically, we're gonna move the whole workshop onto Zoom at this point. And there's a link that has been chatted in Discord to join Zoom for the breakout rooms. And I think that's under the virtual conference sites. So you have to be logged in through the virtual conference, and then you can click there and get to the Zoom.
Okay.
Did that make it out to everyone on YouTube? I don't know.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
Visualizing class separations is used in applications such as classification and clustering. However, many dimension reduction techniques are limited due to the issues of separability and interpretability. We propose a visual analytics framework to support the exploration of nonlinear complex separation structures with the power of locally linear separations.
String graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the string graph layout optimization. The result shows that our algorithms perform better than the others.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results. For example, the Mahalanobis brush and the CNN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
Text alignment is a fundamental technique in many text-related domains. In this survey, we cover 3 text alignment scenarios: collation task, text reuse detection, and translation alignment. On the basis of those scenarios, we reviewed the existing text alignment visualization approaches and discussed their advantages and drawbacks. We finally derived design implications and shed light on related future challenges.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. HyperTendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift. To handle the concept drift, we developed the Drift VIS, a visual analytic system to help the expert understand when, where, and why the drift happens, and update the model to improve performance.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Deep neural networks are vulnerable to maliciously generated adversarial examples.
This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained data path extraction method, a river-based visualization, and a contribution analysis method.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAV, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau, answer questions at the speed of thought.
Attention mechanisms have greatly improved the performance of many language models. Yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
In our current work, we visually compare two cohorts of segmented and classified tissue images.
originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics.